hope you're doing well. This channel provides videos that promote the importance of mathematical modeling techniques. I am currently explaining the 5 characteristics of the Collatz Rope tightrope walking process. In this video, I explain how the parameter R is defined and calculated in order to demonstrate characteristic 3. Under certain conditions, the ratio of even to odd values that appear during the iterative calculation converges to a constant value. Now, consider the ratio R of the numbers of even and odd values that appear in the iterative calculation starting from an arbitrary natural number n sub 0 until the calculated value reaches 1. To obtain this ratio, we must be able to estimate the number of times we divide by 2 required for the even number obtained immediately after applying the TW formula to an arbitrary odd number to become odd again. Therefore, in this video, we rewrite the previously derived Collatz Rope tightrope walking formula in a form that does not include n-1 in the power of 2. These formulas are given as follows. Here, the symbol omega sub I represents the TW formula divided by the odd number h sub I belonging to that Collatz rope. When the calculated value reaches 1, that is, when the odd number for n, that is, h sub n equals 1, the Collatz rope tightrope walking formula is expressed as follows. The term on the left-hand side represents the maximum calculated value obtained under the assumption that all operations using the TW formula increase the calculated value from n sub 0 until it reaches 1. Let q sub 1 super phi be the number of times we must divide this maximum value by 2 to reduce it back to the level of n sub 0. Here, the superscript phi indicates the value of q sub 1 when the coefficient of the TW formula is phi. Similarly, let q sub 2 super phi be the number of times we must divide by 2 to reduce n sub 0 down to the level of 1. The superscript phi indicates the value of q sub 2 when the coefficient of the TW formula is phi. Using these definitions, equation 2 can be rewritten in the following form. Taking the logarithm of both sides of equation 3, we obtain the following equation. Solving this for q sub 1 super phi plus q sub 2 super phi, we obtain the following equation. Below, let n be the number of odd numbers h sub I that appear while the calculated value first increases from n sub 0, then decreases, and finally reaches 1. Let n super asterisk be the number of odd numbers that appear when the calculated value decreases monotonically from n sub 0 to 1. Now, when each h sub I is sufficiently larger than 100 and most calculated values consist of very large natural numbers, the following approximation holds. Under this approximation, equation 5 reduces to the following form. Here, n is the number of odd numbers that appear until the calculated value reaches 1, and therefore n-1 represents the number of times we apply the TW formula using the odd numbers that appear. Let sigma q sub I be the total number of times we divide by 2 for each even number that appears immediately after applying the TW formula until the next odd number appears. We define R as the ratio of this total to the number of times we use the TW formula, that is, n-1. When phi equals 1, The rate of change omega sub I is given by the following equation. Since the increase from n sub 0 is small and q sub 1 super 1 less than 1, we approximate q sub 1 super 1 is approximately equal to 0. Thus, equation 5 reduces to the following form. The ratio R in this case is given by the following equation. Next, when phi equals 3, the rate of change omega sub I takes the following form. Under this condition, equation 5 takes the following form. Using the following relation, substituting equation 9 into equation 12 gives the following equation. Therefore, R in this case is given by the following form. Let us now check the actual values of R for phi equals 1 and phi equals 3. First, consider the example n sub 0 is equal to 56. When phi equals 3, the number of even values appearing in the iterative calculation is 14. Including 56 and the number of odd values, n is 6, including 1. According to equation 15, R takes the following approximate value. On the other hand, since the numerator and denominator of R correspond to the number of even values and the number of odd values excluding 1, that is, n minus 1, R based on these counts takes the following value. Despite the different calculation methods, the two values agree well. Next, when phi equals 1, the number of even values is 6 and the number of odd values is 2, including 1. According to equation 15, R takes the following approximate value. The ratio R, defined as the number of even values divided by the number of odd values excluding 1, that is n minus 1, becomes as follows. These values also agree well. The next example is n sub 0 equals 100, 000 plus 1. When phi equals 3, the number of even values is 61, and the number of odd values is 29. According to equation 15, R takes the following value. The ratio R, defined as the number of even values divided by the number of odd values excluding 1, that is n minus 1, is given as follows. Again, the two values agree well. Next, when phi equals 1, the number of even values is 17 and the number of odd values is 12. According to equation 15, R takes the following value. The ratio R, defined as the number of even values divided by the number of odd values excluding 1, that is, n minus 1, takes the following value. These values also agree well. In summary, this video examined the definition and calculation method of R, the ratio of the numbers of even and odd values appearing in the iterative calculation starting from an arbitrary natural number n sub 0 until the calculated value reaches 1. R is obtained by dividing the number of even values by the number of odd values, excluding the final value 1 minus 1. Therefore, Unless the number of even values becomes sufficiently larger than the number of odd values, the calculated value cannot reach 1. This shows that it depends on the initial value and must satisfy a certain lower bound. As a result, our conserve is an important indicator for judging the validity of the Collatz conjecture. From the analysis in this video, we found that it could be obtained using the numbers of even and odd values appearing during the iterative calculation. Since these counts can be easily obtained while performing the calculation, the computation of R becomes extremely simple. That concludes today's talk. I look forward to seeing you again in the next video. Until then, take care.